Benefits of anti-lock braking systems. Ever since the first automobile accident in 1891, safety in vehicles has been an ongoing field. Anti-lock braking systems, or ABS for short, were originally developed for aerospace in 1930, when it was seen that it could be integrated into motor vehicles. Under braking, if one or more of a vehicle's wheels lock or begins to skid, then this has a number of consequences. The braking distance increases, steering control is lost, and tire wear will be abnormal. The obvious consequence is that an accident is far more likely to occur. Typical ABS components include a vehicle's physical brakes, wheel speed sensors, an electronic control unit or ECU, a brake master cylinder, and a hydraulic modulator with pumps and valves. Technically, the quickest way to stop a car is to put an object, such as a wall, in front of it, but the likelihood of fatality in this scenario is very high. The fastest way to stop a car safely, on the other hand, is by using the frictional force created by the brakes. The greatest form of friction is static friction. A rotating wheel is in contact with the ground under static friction. Therefore, the maximum braking force occurs when the rotating wheel is under the largest resistance. This video describes the different components of an ABS. The first involves the rotational speed sensors, which then tells the ABS's control module how fast the tires are rotating. This control module goes on to have the brakes pulse at a certain speed to maximize control and minimize the stopping distance, allowing the driver to stay in control while they stop the car. Here we have a diagram that shows how the computer of the ABS works. The computer takes into account the vehicle's velocity and the wheel's velocity and puts it into the control algorithm. The brake actuator valve is able to respond if the tires are skidding, and then reduces the pressure to the brakes on the specified wheel. Then the brake actuator rapidly pulses the affected brake, and the load on the brake is reduced, allowing the wheel to regain traction. Stopping distance. We see that without ABS, the tires lock, causing the wheels to slide, and therefore preventing the driver from turning to avoid hazards in the road. With ABS, on the other hand, the sensors detect the brake lockup and pulses the brake to prevent it from locking and skidding, allowing the driver to maintain control of the car and avoid the hazards in the road. As seen in this video, anti-lock braking systems have proven their effectiveness time and time again. From this chart, we can see that as a vehicle's speed increases on wet or dry surfaces, the stopping distance also increases. However, when ABS is compared to no ABS, we can see that in vehicles with ABS, their braking distance is minimized. When road conditions become less optimal, such as on a rainy day when the roads become wet, it is clear that ABS has a greater impact in reducing stopping distance. Taking the comparison between ABS and no ABS at 110 km per hour on wet road conditions, ABS has a much lower stopping distance of about 13 meters. For every speed a car travels, there's a minimum stopping distance, and anti-lock braking systems allow this to be achieved because it creates the maximum braking force. The average results with ABS provided an overall reduction in stopping distance of about 5%, according to a paper authored by Donovan Green. Stopping distance is almost always longer with locked or skidding wheels, which is prevented by anti-lock braking systems, and ABS halves the risk of causing a rear-end collision. Traction. The task of keeping the wheels operating at maximum traction is complicated, given that the friction slip curve changes with vehicle, tire, and road conditions, Amin writes. Some computers anticipate the upcoming values of wheel slip for desired values, using multiple sensors and software programs. The ABS computer itself accounts for various factors to guarantee maximum traction, including the slippage of the wheels, the speed the wheel is rotating, and the optimal rotation of each wheel to maintain control. Steering and control. By prevention of wheel lockup, ABS enables the driver to maintain steering control during emergency braking. From the position of braking performance, driving comfort, and anti-lock braking system control performance, the configuration with the combined electric and hydraulic actuators is significantly better than the conventional solutions with friction brakes and rule-based ABS algorithms, Savitsky writes in his article. A simple but accurate example of maintaining directional control can be seen in the picture, where the car with the anti-lock braking system can maintain directional control and avoid the deadly traffic cone. According to the National Highway Traffic Safety Administration, ABS works with your regular braking system by automatically pumping them. In vehicles not equipped with ABS, the driver has to manually pump the brakes to prevent wheel lockup. In vehicles equipped with ABS, however, your foot should remain firmly planted on the brake pedal, while ABS pumps the brakes for you so you can concentrate on steering to safety. Essentially, anti-lock braking systems automate what could be considered a complicated driving maneuver. And finally, just to reiterate, we've discussed how ABS brakes came about, what anti-lock braking systems are and their benefits, and how anti-lock braking systems affect the stopping distance, traction, and steering and control of a motor vehicle.